So today's problem is the driver of an SUV of mass 1,700 kilograms isn't paying attention and rear-ends a car of mass 950 kilograms at a red light. On impact, both drivers lock their brakes. The SUV and car stick together and travel a distance of 8.2 meters before stopping. How fast was the SUV traveling before the collision with the coefficient of friction between the tires and road of 0.72? After reading the problem, box or circle any of the given. We've circled mass of the first SUV of 1,700 kilograms. Next, we circled the mass of the car of 950 kilograms. Next, we underlined that the drivers lock their brakes and the cars stick together, which is valuable information. Next, we boxed the 8.2 meters that they traveled before stopping, which is underlined. The two items that are starred are how fast, because we must find the velocity of the SUV before colliding with the car. And we box the kinetic coefficient of 0.72. After, we should write our givens. Our first given is the mass of the SUV. Our second given is the mass of the car. The initial velocity of the car was 0 meters per second, since it was already stopped at the red light. We are trying to find the initial velocity of the SUV. The final velocity for both cars is 0 meters per second. The total mass for both cars is 2,650 kilograms. And lastly, we know the mu, or the coefficient of friction, of 0.72. Before starting the problem, we must understand that there are non-conservative forces acting on this collision, and that force is the friction between the road and the tires. In a situation like this, energy is converted to another form. Since we have speeds and positions, you can relate the two at two different points. Then you can use conservation of energy because you know position and stopping force and distance, then you know how much work is being done on both vehicles. With this being said, you can relate to kinetic energy of the car and SUV. Based on all this information, energy is not conserved, it's conserved. But in order to better understand, we must draw it out. So at position 1, the car is traveling at an unknown velocity, which is what we're trying to find. But we know the mass of 1,700 kilograms. And the SUV is represented by a box. The car is represented by a circle, and we know that the velocity of the car is 0 meters per second because we know that it was already stopped. The mass of the car is 950 kilograms, which is already given. At position 2, we have both the SUV and the car moving with the same velocity that we don't know, which is what we'll try to figure out first. But we know that the mass in total is 2,650 kilograms, and the distance it travels between that and position 3 is 8.2 meters. At the end, or when the cars have come to rest, both the SUV and the car have a velocity of 0 meters per second, and the total mass is 2,600. Since the kinetic energy in the collision is not conserved, we must first figure out the kinetic energy at position 2 that we previously drew, the kinetic energy at position 3, and the work done by the non-conservative forces, giving us the equation that the kinetic energy at position 2 is equal to the kinetic energy at position 3 minus the work by the non-conservative forces. This equation further breaks down into 1/2 m total v at position 2 squared, because kinetic energy is 1/2 mv squared. Kinetic energy at position 3 is then 1/2 m total the velocity at position 3 is squared minus the work of non-conservative forces, which is f d cosine theta, which then translates, since the force acting upon the system is friction, it equals to u m total g times distance times cosine theta. Once we continue to break it down, we continue with 1/2 m total velocity at the second position squared is equal to 0, because the kinetic energy at position 3 is 0. Since the velocity is 0, therefore multiplying by 0 would give you 0. Minus the coefficient of kinetic friction, the mass total, multiplied by g, times the distance times cosine theta. We are using mg here in the situation for the force because the only force acting on the cars is on the SUV is the force of gravity, which is equal to m. Since both sides of the equation both had m total, they can be crossed out since they're on both sides, and they can be disregarded. Our new equation would be 1/2 velocity at the second position squared is equal to a negative coefficient of friction times the acceleration of gravity, which is represented by g, the distance traveled by both cars, times the cosine. We can now insert for the things we know, which are the coefficient of friction, the acceleration of gravity, the distance, and the cosine theta, which would be equal to 180 since this is all happening on a straight path. So now we have 1/2 times the velocity at the second position squared is equal to negative 0.72 times 9.8 meters per second squared times 8.2 meters times the cosine of 180. After doing algebra by multiplying the 1/2 over equation would then be v in the second position squared is equal to 2 times, since we isolated v squared by multiplying by 2 to get rid of the 1/2, times a negative 0.72 times 9.8 meters per second times 8.2 meters times the negative 1, because the cosine of 180 is negative 1. The resultant of that equation is velocity at the second position squared is equal to 116 meters squared per second squared. We must then take the square root of both sides in order to get rid of the squared and isolate the velocity at the second position, and as well as reduce the meters squared per second squared. The resulting is the velocity at the second position is equal to 10.8. After finding the kinetic energy, after using kinetic energy to find the velocity at the second position, we can now say that the momentum between position 1 and 2 are equal, because both cars at position 2 are moving based on the momentum of the first car in position 1. For position 1, we have the mass of the SUV times the velocity of the SUV initially, plus the mass of the car times its velocity of the car. This further breaks down into the mass of the SUV times the velocity of the SUV plus 0, since the velocity of the car is 0, and multiplying by 0 results in 0. Moving on to the momentum at position 2, we have the mass total for both the SUV and the car times the velocity at position 2 that we found before using kinetic energy. The final equation we can use is m of the SUV, the velocity of the SUV, is equal to the mass total times velocity. In order to isolate the velocity of the SUV at position 1, you divide by the mass of the SUV. So now our new equation is the velocity of the SUV at position 1 is equal to the mass of the total mass times the velocity at position 2 over the mass of the SUV at position 1 is equal to 2,650 kilograms, which is the mass total, times 10.8 meters per second, which was the velocity at the second position, over the mass of the SUV, which is 1,700 kilograms. To know if we're on the right track, since kilogram is both on the bottom and on the top, we can cross it out, and you're only left with meters per second, which is the unit we want to find velocity. Before we get the velocity of the SUV, we have 28,600 meters per second divided by 1,000. We have the velocity of the SUV at position 1, or its initial velocity before colliding with the car, at 17 meters per second.